Hello everyone and welcome to the Autodesk Robot Structural Analysis tutorial brought to you by the Civil Engineering Essentials channel. I hope you enjoy the video. Alright, welcome to the second part of the basement wall in which we are going to talk about the design of those things. Now just to recap, we did the following to the basement wall. In part 1 we basically talked about the principle of a basement wall as well as a quick model in that part. I realized very quickly that those were rafts, so I modified them. Nonetheless, we're going to continue talking about this. Now, please notice that I told you before that I'm a shell guy. I love the shell. And I used I think I modeled most of them using the wall command and then only modeled those using the floor command. Let me show you what I mean. If you click here and select all, you can see those wall commands are being used here. Now, you will soon realize that this is not the way to do it, but I did this because people kept asking me, hey, why don't you use wall? And I will show you why I do not use wall in a moment. So, as a spoiler, we're going to regret that. Before we design, our mesh looks a little bit too coarse. The reason why it is too coarse is because I didn't make it fine or normal. So I go to my mesh settings and use the normal settings here to do my mesh. Now, why do I use coarse? Because when I do a preliminary model, I want to check if a model is working and if no instabilities are there. Question number 2, why do I have those little things? I have those little mesh inconsistencies because you can see it's struggling to mesh the corner here because the wall was not reaching the end. Why didn't it reach the end? Because, well, I think I was talking about having an empty space here, or maybe you want to make a release. It can happen, so please double check part 1 to see exactly what the idea behind this was. So I run the analysis now. Now, with that being said, well, my analysis is complete. So of course, now I'm assuming that you have seen the slab series. It's a 5-part series. It will be linked above, in which we talked about how to design those slabs. And you can use the slab series to design that thing, which is perfectly fine. Now, I will be talking about the provided reinforcement here. Of course, if you go to results maps, then you can show up the MXX and the MYY, and you can see the moments on that thing. Now notice, you see nothing. Yeah, wait, that's a dead load. It doesn't make any sense to open the moment. Okay, wait, okay, cancel everything. That was a dead load, and the dead load will have limited moments actually. So let me just open the earth load, which is the lateral load here, because dead loads will basically be the loads from the dead loads on the structure. But where you really see the moments is on the earth pressure. My bad, I was selecting the incorrect case. Of course, the editor is not going to make fun of me. I totally see this. I can see the future. So now I'm selecting the earth case, which is the lateral case, and now it should be making sense. So let's go to MXX, hit the apply button, and now it makes sense. Now it's correct. Now this is what I was expecting. So you can see the MXX here being a bit more pronounced than here because you have an edge here, you have an open edge here, so the edge wants to open up, which means that because it's not constrained by the slab, which means that you have more moments here. Now, of course, to go to MYY, yeah, now it makes sense. The previous one was like, scrap that. It didn't make any sense to me. You can see the stresses burning in the base, and of course, here you have some stresses because you have a connection with the slab or the beam, whereas here you have zero stresses because there is no connection. You have stresses here and moments here. I mean, stresses are moments, so you have moments here because it's connected, moments here because it's connected, and you have zero moments here because there is no connection. You have some moments here because there is indeed a connection with the column. So everything seems to be fine and seems to be making sense. However, you will be surprised when we design that thing. So let's go into the design of those things. Now, how do we design that? I am not talking about the required reinforcement. For the required reinforcement for slabs or shells, as well as walls, there is a video that is going to be linked above, as well as, of course, the slab series I just mentioned before. Yeah, you should double check that because it really helps you understand everything, including the meshing. So it's kind of an important thing to take a look at. Anyway, to continue here, I go to provided reinforcement immediately. And from the get-go, I will select those walls. So I'll select this wall. And you will realize it will not work. As strange as it sounds, I know it is called a basement wall. But when you design the basement wall, it will not work if you use a wall for the basement wall. So let me show you that. Now if I click here and go to design and ask it to give me provide reinforcement for that thing, now this is what happens. It just opens you a wall. As you can see, it imports the wall. And I'm going to import, of course, the simple cases. Notice that in the ASI code, there is no special case for earth, so I think I will assume it to be dead load. And this is important to mention because maybe you are using a different code, and if you are using a different code, then you might run into the idea that earth loads are different than dead loads. In this case, you cannot have them in the same category, and you would have to make manual combination and add the earth into it. Allow me to explain this and show this to you. So I'll cancel that now very quickly. Assume that you have a code that does have a provision for the earth load. So how could you deal with it in Robot? Now you would go to, for example, manual combination here if you want, and you could add a combination as ULS. And then you could put manually, if you want, the load factors here, and just create your own combination and apply that. And when you import the wall, you will have to select the combinations as you import. I have seen some strange code. Let me just double check my codes here. So design code. Okay, reinforce concrete offline. Okay, I just thought I saw some strange code for combination. Yeah, I think I saw a strange code for combination. Okay. So anyway, just double check my code. Of course, I'm assuming that you know how to set your preferences. So if you don't know that, there is a link on the top right where you can just set up your units and preferences. Anyway, let's get back to business. So now you would think, wait a minute, why are you selecting one wall? Shouldn't you select the entire wall as one unit? And you're right, I should select the entire wall as one unit, but there is a problem in Autodesk Robot when you do that. If you select 3 walls, and you have drawn the walls element by element, piece by piece like this, something very strange, very peculiar happens with the robot. If you go to design, provide reinforcement of reinforced concrete elements, of course, now remember you can select manual combination if you want. I'll still stay with simple cases. If you click on OK now, it doesn't import all the 3 walls as one wall. Rather, it imports each wall separately, which is kind of odd because it's one unit and you would have steel bars extending from one wall to the other. I mean, look, you would have steel bars just extending the entire length. But Robot doesn't understand this. Robot just takes it as a wall. Now, why should you not use the wall? You should not use the wall because this module doesn't work at all. This module for wall works when you have a shear wall or a bearing wall. It doesn't work at all if you have a basement wall. It doesn't work at all if you have a retaining wall. As strange as it sounds, although the retaining wall and basement wall have the word wall in them, using the wall and modeling that thing will not work at all. You want proof for this? Go to wall load pattern. This is how you can input the wall loads, and if you take a look, those are the loads that are imported into the wall. What do you see? You see a normal force, which is the vertical force. You see a horizontal force, and you see a moment that basically tries to break it off. And this is characteristic to a shear wall. Do you not believe me? Well, let's run the analysis and go to wall results or reinforcement, and you can see the reinforcement pattern being exactly as a shear wall, not a basement wall. There is a total, there is a total disconnect between what we saw in the moment here. Allow me to explain it to you. So let me just show you that very quickly. You select earth and then you select those 3 walls, for example, just showing you, or you select all those walls. Now you go to results, maps, and just show them in a new window to just kind of fix the scales. Look, you can see there are moments here, burning moments in X. You can see that there are burning moments in Y, but those moments are not at all addressed in your reinforced concrete design when you select a wall. It doesn't exist, it doesn't see it. Why doesn't the wall see it? Because the wall module is not programmed to deal with moments XX and moment YY, moments that try to bend it in the plane. It doesn't work like that. It's programmed to deal with those loads, which are typical for a shear wall, not a basement wall, and not a retaining wall. So the wall module works when you have a shear wall and a bearing wall, which carries vertical loads. It doesn't work at all if you have a basement wall or a retaining wall. In other words, if you have any wall where the load is perpendicular to the surface of the wall, then the wall module is not the module you should go to. This is a no-go at all. You should not even touch that. So I hope that you learn this, because it's very important to understand this, because every time they ask me, like I see some viewers asking me about why am I not using the wall module in my retaining wall before. So that's the answer now. All right, so it seems I messed up. It seems that I messed up. So how can we unmess up? Well, let me just check if I have a quick fix for this. I really don't know. I need to check that now. So everything that is a wall seems to be messed up. So let's right click here and select all. Now I select all my walls. I need to magically make them become shells. And well, how do I do that? Structure, you can see wall here. Oh, I think I can fix that. Should I select floor or panel? I don't know. I can very easily cheat. If I click here, the structure type is a floor. So I will right click here, select all, and select the floor. And now I have fixed the problem. Now they are all considered floors, not walls. In other words, if I select this, this, and this, and then go to design provided reinforcement, of course I will just take the cases here and just run the analysis. Okay, first of all, it took them as one unit. So the first good news here is that it took the entire wall, aka shell in this case, as one unit. So if I run the analysis now, hoping everything works, now I'm just running a blind analysis, everything seems to be working, and it designed them using wire meshes. Now, I had a full slab series talking about this, but for now, I'll just go to here, reinforcement thing, and I'll select it to be bars, okay, and I'll calculate again because I want to have bars. I'm a bar fan. Now, if you go to your reinforced concrete design slab reinforcement, you will be surprised of the details. Look how beautiful this is. This is gold here. And you can understand why I was really hating walls. Now, the wall here is still available, but it's, of course, now this is out of date because you have slab 41 to 43. So take a look at the wall that is now outdated. It doesn't exist. But look at it. Okay. See, it doesn't even see those moment variations. Look at the reinforcement. This is nuts. And the crazy part is, like the thing that's unbelievable here, is that Robot doesn't even raise an issue. If you go to the note, it says everything is perfectly fine. It shows the required reinforcement, the provided reinforcement gives you all greens, and everything seems to be fine. And this, ladies and gentlemen, is why using software as black boxes is dangerous. Allow me to take some of your time just to explain this to you. Look, what I'm trying to say is, it is extremely dangerous to just say, hey, I'm using the software, everything is fine. Because look, I just used the software and I used a wall here. Using the software just because the software works is not the way to go. You cannot simply use a software just because it works, because it can mislead you if you do not understand the inner workings of the software. So understanding the inner workings of a software is much, much more important than producing cool drawings and cool results. I mean, look, it's really amazing. And if you go to the wall note, everything is perfect. If you go to the reinforcement drawing, you have professional stuff. Unfortunately, this professional stuff is basically garbage. I'm sorry to say this, but this is like not what you should have done. And it's basic. However, this professional stuff is basically useless. The reason why it's useless is because it's based on a totally bogus assumption. The assumption here in the load wall pattern is that there is no perpendicular loads on the wall, and it doesn't see the MXX and MYY moments at all. And that's the reason why this is absolutely unacceptable. And even if the program tells you everything is fine, you should not. Of course, you have this channel, Civil Engineering Essentials, to warn you about. And if you think that this was a good warning, then of course, like, share, comment, subscribe, and suggest this channel to your colleagues. Now, the second weak point in walls is basically that it deals with each wall on its own. Now, this doesn't make sense in our structure, but it makes perfect sense in a shear wall or bearing wall situation, because your shear walls are walls by unit walls. They are not just connected to one big wall. Now, if you go back to the slab, you can see that this problem has been mitigated, has been resolved. If you go to slab reinforcement, you see everything being perfectly fine. You see there is an increase in the horizontal steel at the columns because you have seen that there was higher moments near the columns. You can see in positive and negative some differences in steel. That's cool, that's great. So I think that I'm happy now. Uh, of course, that's one slab. I need to do all the basement walls. So let me go to the structure model now and go to geometry and select me another wall. So I just select those 3 walls now. The cool thing about if you select 3 shells or slabs and then you ask it to design it, it understands you are talking about 1 unit and it takes them all as 1 unit and even provides you with a continuous steel bar. Allow me to explain. Now I have a new wall. I'm just going to run the analysis. I hope I still. Oh, I think I need to. Oh, that's annoying. I need to do this for everything I import. That's kind of annoying. Okay, fine. Let me run the analysis again. Now let's go to reinforced concrete design slab reinforcement, and let's take a look. Now, of course, there is a difference in steel here because, well, in this case, you have a different loading condition. Now, I am really thrilled and happy about this, and this is really golden. Allow me to explain this to you. Now, first of all, if you click here, no, not this, if you select this horizontal steel, you can see Robot is putting 1 piece here. Now, why didn't Robot put 1 piece from the beginning to the end entirely? The reason why Robot didn't do that is because the wall was 15 meters long, whereas your steel bar as provided here was 12 meters long. Of course, if you have steel bars in your region that are 18 meters long, be my guest and put 18 meters here. Now, Robot is using 12-meter bars, and that's why it's unable to cover the entire length using 12-meter bars. So it breaks the bars. Now, you would think that this is wasting money. You would think that you should break it like this. You should break it in 1 point because whenever you break a steel bar, you need to provide development length, which means you need to provide steel, which means cost. You would think you can break it in 1 piece like this, but you cannot, truth to be said. Why? This is the negative steel, this is the negative side, and this is the positive side. Now, when you break a reinforcement, you need to break it in points where you have minimum moments or minimum stresses on the bar. Now, in the negative reinforcement, it was breaking it above the support because it was not required there. But if you go to the positive steel, it is not breaking it above the support. It's actually breaking it in the middle of the span. And this is really, really smart because Robot is now trying not only to provide the reinforcement on the entire wall, it also tries to break the reinforcement in exactly the right places. And this is genius for me. Like, this is next level. It's very easy as an engineer to just shove it on the site engineer and just say, hey, I want this, and just give him this drawing and that's it or something. And then let the site engineer just work it out himself. But giving him those drawings with those details is really next level. Like, you can really be happy when you give that to the site engineer, and he shall be happy too. So yeah, I think that I am genuinely happy now. And there is nothing I want to add here. So I want to go back now and just wrap it up again. To issue a stern warning, please do not, as tempting as it sounds to use walls, do not use walls when you have an area element with forces perpendicular to the surface of the element, because walls do not see those moments. Walls only see axial forces and see moments that are around the vertical axis of the wall. What do I mean by this? Let me draw the wall in 3D. Okay, so the difference between the floor and the wall is that the floor feels like the floor is being designed having in mind the following forces. The forces in Y as normal forces, the forces in X as normal forces, which will cause compression and tension on the wall, requiring steel. Of course, those axial forces will provide steel equally in the outside surface or face and the inside face, so basically on both sides. It also feels the force in the z-axis perpendicular to that element. Of course, the z-axis here is the local z-axis. And this force will provide it with shear stresses that needs to be checked against the concrete strength. It also feels the moment around xx, which is the bending moment in this, the moment around YY, which is the bending moment here. And unfortunately, if you're using a shell element, it might struggle understanding the moment around this axis. It depends, of course, on the assumptions of the shell element, but sometimes it struggles for the moment around the z-axis. Now, this is what a floor element feels. A shear wall doesn't feel any of that. A shear wall just feels three forces: an axial force here, a shear force here, and the moment being around this, like around this axis. Let me just draw it. If you have an axis here, the moment around this axis from earthquake. Now, how does it design it? Well, the moment here is being mainly resisted by something called the boundary element here, so the steel here, which will provide compression forces, and the steel here, which will provide tensile forces. And that's the reason why you can see shear walls having boundary elements where a lot of steel is being concentrated on those elements. So it's kind of a different paradigm between those two elements, kind of a different theory. And you should use floors if you have anything that has forces, mainly forces perpendicular to it. Examples being, well, everything here. A slab is an example where you have forces perpendicular to the element. And of course, basement walls and retaining walls are another example. So I hope that this comparison makes sense. I know this video might be of short format, but I think I have talked about everything I wanted to talk about today. So we have modeled in part 1 the basement wall, and in part 2 we have designed the basement wall. And of course, I could just waste your time by showing you more details here. As a matter of fact, I will right now do that. So, but I just think that your time is like too valuable, and you can check it out yourself. But of course, like with the next steps would just to go here in the calculation note, show the calculation note here. Everything is green, but this time everything is indeed green, and everything is fine. If you go to drawing, of course, you can export the drawings. Everything is fine. And do not be tricked by the wall. It seems everything is fine in the wall, but it isn't. So don't let it trick you. Of course, the wall here, and even if you see cool drawings for the wall, those are just looking cool, nothing else. This is not true. So yeah, that's everything I wanted to talk about. I hope that you enjoyed the video and that it was beneficial for you. Of course, if you have enjoyed the video, then please like, share, subscribe, and comment, especially subscribing, because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel, and we'll catch you in the next video.